possible. And I want to welcome you again to this event here at Evangelical Community Church. We're delighted that you came. For those of you who were here last week, and for those who were not, just a reminder about last week. Last week we did session number 1, entitled Sacred Ground, Evangelical Perspectives on Creation Care. That was by Dr. Jessica Mormon. She did a wonderful job, and we've heard a lot of positive feedback about that. Tonight, our topic is from a scientific perspective. It's called Our Changing Planet, the scientific perspective on climate change, and our keynote speaker is Dr. Ben Bramson. Many of you know Ben from him being around here for the last 150 years or so. Ben's been here forever, and it's a delight to have him, but later Michael will introduce him. I've been given the responsibility of reminding you of a few things. On your table, there's actually 2 things that I want to call to your attention. One is a further resources piece of paper, so you can take a look at more resources related to this topic. Also, there's a glossary lexicon of scientific terms on the table. We thought this was especially important for tonight's event because there might be words that you're unfamiliar with. Just to once again thanks Michael Hamburger and Adrian Keller and Dan Law, and Clay Lickers is somewhere. He's not. He's back there somewhere. He will be filming this event as well as that pool camera. So if you'd rather not be on video, we have those yellow video cards back there at the back that say no video. Otherwise, you may be on a film that will be produced by my son later on. Food and drink are available. You notice that. You can feel free to mill about and go back there as you wish. We are going to use, as we did last week, a piece of technology called Poll Everywhere. It was introduced to you by Krista. We had a few bumps along the way in our technology, and tonight it will be flawless. We got the word on that. No, don't expect that. Technology is just a bit demonic. But anyway, we're going to use Poll Everywhere, and you're going to see a Poll Everywhere option up here when Krista opens up. Here's the key, okay? Listen carefully. Whenever she's up here doing her thing, do not text questions that are on your table to that number for the purpose of an answer from the panel. We're going to wait on that, okay? So do your work with Krista when she's up here. Once that's over, stop texting, and then wait till Ben gets up here to do his lecture. As soon as he opens up and says, hello, my name is Ben Bramson, you can start firing questions at him. And they're going to be collected, and then we're going to bring them up a little later on. Our last event I wanted to also mention is Sunday. This Sunday, it's going to be at McCormick's Creek from 2 to 6. We're looking forward to seeing all of you there and some others as well. Yeah, so 2 to 6. There's a $7 entrance fee to get into the park, and if any of you wish to carpool, some of us are going to meet out here in the parking lot at about 1:30. So if you'd like to save a little bit of change, you can find a friend and go out there with them. From about 2:15 to 3, we're going to have a group session, which will include singing. From 3 to 4:30, we're going to have a hike, either down to the canyon or a waterfall hike, and we're going to do some bird banding. That ought to be great. Then we're going to have a fellowship meal from 4:45 to 5:30 and a final discussion from 5:30 to 6. All of those times are subject to change, but that's our best estimate, okay? We hope you will be there. Thanks for coming. I'll turn it over to those who know what's really going on.
Thank you guys for coming back. I woke up in the middle of the night thinking it would just be me and Bob and Adrian here this evening, and I'm so pleased to see everybody back here. I don't know what you guys, but I felt so great after last week's discussion, presentations and discussion. I feel like we're really getting into some rich material. So thanks for coming back for more. I hope we see all of you on Sunday. I think that's going to be a great kind of culminating event. From my perspective, opening up with last week's event was really kind of giving a broad perspective about connecting all of the dots in the life of faith and giving some very strong reasons why we should care. I think this week's presentations and discussions are getting into some of the specifics of environmental stewardship, about why we should care, about the things that we should be concerned about and what we might do about them. So I hope that's going to generate some really lively discussion. I forgot to say who I am. I'm Michael Hamburger, Department of Earth and Atmospheric Sciences. I'm so grateful to all of you for coming, and especially for Pastor Bob Whitaker, Dan Waugh, and all the staff of the ECC for making such a welcoming home for us. How about a round of applause for them? And I forgot two important acknowledgments last week. One was to mention that part of the idea for this workshop and support for the workshop actually grew out of a program run by the American Association for the Advancement of Science called the Dialogue on Science, Ethics, and Religion. And they provided a grant that's paying for some of the Reese's cups on your table and on Sunday. So that has been a great source of support and part of that community. I also neglected to mention Adrian Keller, who has been a partner through actually the whole history of the Concerned Scientists organization and has been a strong force behind these workshops and is now a leader of our new student-led organization, Advocates for Science at IU. So for those of you, especially students, who might be interested in learning more about that, collar Adrian at the end of the meeting and learn some more about it. Okay, Krista is going to say a word about the poll everywhere, and then I'll say a word about our speakers. So Krista Hoffman-Longton from IUPUI.
Thank you, Michael, and thanks again to Pastor Bob and the ECC community. We feel incredibly welcome here, and I think that it's a testament to the amazing community that exists at this church, as well as the community that exists here at IU. So we started last week with a couple of Poll Everywhere questions. For those of you who are not familiar, Poll Everywhere is a tool that you can use to gather some perspectives from individuals in a room. And you can do that anonymously. And that's helpful for a conversation like this, where we don't know one another maybe as well as we'd like to yet, but this gives us a chance to get to know one another. It brings our perspectives together and helps to draw out a sense of who is in the room with us. So if you've never used Poll Everywhere before, it's relatively easy, but getting kind of into it is a little challenging. So I'm here to give you some instructions. So you want to go ahead and open that one for me, Dan? Okay. So if you take a look, and if you have a smartphone, or if you have a not so smartphone, but can text, this will still work for you. So here's what you're going to do. You're going to get up your phone, and you know how you text your mom or your best friend. The person that you're going to text you're going to text 22333. So think of that as the phone number that you're going to text to. So 22333 is what you put in that top line for kind of who you want to contact. And then to join the poll, you're going to text to that number the word T Fellowship 433. So the message that you'll send to our new friend, 22333, is T Fellowship 433. That should invite you into the poll, and then when that happens, you can respond to this question. What word comes to mind when you think of climate change? And if you use just one word, you'll see words sort of get bigger as more individuals put those words in, or get smaller as maybe we have one individual in the room put those words in. And so what I like about this tool is it gives us a sense of the perspectives in the room and how big or small those perspectives are. And if you've got a couple of words, you can certainly text another word, and that will show up, even though it says just one. So it looks like urgent is a word that has come up at least a few times, also crisis, complicated. And I think that these are powerful because it helps us to think about really why we're here, right? This is a really complicated issue that we know will require lots of different perspectives and ideas to think about and to solve. And so having a sense of your feelings or your perspectives about this will help not only all of us as we further our conversation, but also our speakers, our panelists who will speak tonight, get a sense of what some of your concerns are. We've got a couple more questions for you, and I shared last week that these questions come from the Yale Climate Survey. So Yale University runs a survey very regularly to get a sense of where the US population is related to the concept of climate change. So if we go to our next question, and that question is, and you're going to use the same strategy you used before to text, but this time, instead of texting a word, you're just going to text the letter of your answer. So this question is, assuming global warming is happening, do you think it is A, caused mostly by human activities, B, caused mostly by natural changes in the environment, C, don't know, or D, other? So you can just respond to that initial text that you sent with either A, B, C, or D, based on your perspective. Now it looks like we've got a few folks in the B and C category who are still thinking through some things. Lots of folks are talking about the idea that that's caused mostly by human activities. And again, this helps us sort of get a perspective for how folks are feeling in the room right now. So let's go to the next one. We'll go ahead and go to the next question. Great. And that one is, which comes closest to your own view? A, most scientists think global warming is happening. B, there is a lot of disagreement among scientists about whether or not global warming is happening. Or C, I don't really know enough to say. And again, it looks like we've got a few more perspectives around the room. If we want to go ahead and close that poll now, I'll just say some final words and then I'll turn the mic back over to Michael. We know that these conversations are not easy for everyone, but they are powerful and important. And so I want to encourage all of you to thank one another for showing up here tonight, showing up here with one another and being in the room. We have lots of varied perspectives in the room, and that's one of the things that makes this type of approach to conversation so powerful. After you hear our panelists and our keynote speaker, our primary speaker for the night, we'll have a chance to get to know one another at our tables and answer some questions that don't have necessarily right or wrong answers. And I hope that you'll see that as an opportunity to get to know one another. Adrian and I were talking a little bit earlier about the idea that I use a lot of improv theater techniques to lead discussions, even challenging discussions. And one of my favorite metaphors that improv uses is the idea of bring a brick, not a cathedral. That when you come to a conversation, rather than bringing your beautiful cathedral all planned out and ready to go, sometimes it's valuable to bring one brick and have another person bring another brick, and that's how your cathedral is built. And I think that that's the goal that we have for our conversation tonight, really focusing on the values that we share and the collaborative opportunity we have together. So with that, I'll turn it back over to Michael. He'll introduce our speakers, and we'll get some information to you. Thank you.
All right, thank you. A round of applause. During Ben's talk and the panel discussion, we invite you to submit questions using the same text messaging, but you're not allowed to ask a question until Ben finishes his first sentence. After that, it's open for questions. We're not going to do long-winded introductions here. I'm going to ask the speakers to say a little bit about their own background, what brought them here. I'll just say a word about Ben. He's one of the coolest people I've met since I've come to Bloomington 33 years ago. He is a research superstar, an amazing instructor, and a great community leader. And while I was searching around a little bit for a CV today, this is going to be a little embarrassing. I happened to first link that came up with his name was ratemyprofessors.com, which is a really horrid thing where all my students come to complain about how much homework they have or something like that. The first one I came across said, Dr. Brabson was my favorite professor that I ever had at IU. He is brilliant, compassionate, and is out to change the world bit by bit, student by student. I know it sounds really cheesy, but he is a modern day hero. I took his class 10 years ago, and this walk back on to say how much he inspired me in environmental physics. Is that the dream of every professor? Thank you for helping change the world.
Marvelous, lovely. Michael, what can I say? That was simply, that is the loveliest introduction I've ever had, I must say. What a pleasure to be here, and I'm delighted that you're here. And you tell me if this microphone is too loud. Usually what I do is I put it right in my mouth, and that's not good. And so if you can't hear me back there, just raise a hand or do something, because I'm likely to overdo it rather than underdo it. Very good. So one of my favorite people is sitting right here, and her name is Ellie McFarland, now McDonald, and she was married to Malcolm, who was a member of this church and a great educator of the highest rank at Indiana University. I must say, all those words which were read for me should have been read for Malcolm, quite frankly. So lovely folks. So let's get started and talk immediately about three things. They have to do with climate, and they have to do with the science of climate. And so I'm going to ask you to stick with me for the next 20 minutes, or shortly thereof. And if I can start things up, I think I can do it here by pushing this. Let's see what happens. Well, that was in this morning's paper, so I thought I would just put that up there. It just says we talk about record heat, record storms, record floods, and of course my research turns out to be in extreme temperatures, which you know, and it's coming extreme temperatures coming from the Midwest, and in particular those that are associated with soil moisture. It turns out that soil moisture is something which is really important. It's important because it is our ocean. People who live near the ocean have a moderator in the ocean. Water, because water is evaporating typically from the ocean and absorbs a good portion of the solar energy that's coming from the sun. Since we don't have an ocean, it turns out water vapor is important, and not surprisingly, you're going to get really, really hot days when you don't have much soil moisture. So we've had a couple of hot days recently. Have you noticed that there actually isn't very much soil moisture? Those two go very well together. Okay, well, so what I'm going to do is talk about three things. I'm going to talk about first temperature, second carbon dioxide, and then third fuels. Those three things and only three things. So this will be an easy thing to put away in my view. Following that, then Gabe Filippelli, Ellen Henderson, Paul Staten, and Kim Novick will talk then about individual pieces of this puzzle, and they will then introduce themselves. So let's get started. Okay, let me give you my conclusion at the beginning. Here is my conclusion, and I read it to you. It says that we are obliged to move away from our own non-sustainable and climate-damaging fossil fuel use as quickly as possible, and that we're clever enough to figure out how to do that. Okay? So those are people lying on the sidewalk. They're not dead. They look dead, but they're not. This comes from an article that was published in the New York Times on May 30th of 2018. It turns out that there was a record temperature which was achieved in Pakistan, in a small village in Pakistan, whose name I will not try to pronounce. It was 122.4 degrees Fahrenheit, which indeed is the highest temperature recorded anywhere. So what's going on? Well, we're talking about temperature, so let's take a look at existing temperatures. Before I do that, I'm just going to quote two pieces from the Intergovernmental Panel on Climate Change, which comes from an old version back in 2014, and I read them to you. It says about past warming. Warming of the climate system is unequivocal. Interesting use of the word. Do scientists use the word unequivocal? Almost never. Very interesting that it's used here. Second detail, human influence. Human influence on the climate system is clear and recent anthropogenic, that is, human emissions of greenhouse gases are at the highest level in history. Recent climate changes have widespread impacts on human and natural systems. There will be another IPCC full report which comes out then in about 2021, in about 2 years' time, and so this is the one which is now 35 years old. Okay, there is one other detail that did happen in the last few days, and that is there was an IPCC report specifically on the ocean and the details of what is called the cryosphere. This is a statement which, the first of which is a little pessimistic, the second of which is slightly less pessimistic, a little bit more optimistic, but I think it's worth putting in perspective the present situation, which is not pleasant. And I read it to you again. This is coming from part of that report. This is the executive part of that report, a piece of that. Ocean warming, okay? And acidification, and deoxygenation, ice sheets, glacier mass loss, and permafrost degradation are expected to be irreversible on timescales relevant to human societies and ecosystems. That's about as depressing as you can get. It says basically there ain't nothing we can do about it, which is really kind of scary. Now, one has to keep that in mind that they're talking specifically about the frozen portion, typically, and the ocean portion of our world, which is not necessarily all of our world. Let me read you the second piece, which is slightly more optimistic. It says that ocean-based local mitigation and adaptation measures are useful to implement because they address global risks and often have co-benefits such as the biodiversity conservation and will reduce the need and cost of adaptation. So part of the business that we're up against here is that if climate change does indeed continue, then indeed we're going to be obliged to do not only the business of mitigation, that is trying to slow climate change, but also adaptation. But we have to actually change the way we behave in order to cope in a heated world. Okay, so there are two pieces which are pretty terrifying. Let's look at some data. These are temperature data over the last 120 years. And what you see here is that there is a little peak, and I can use my little laser pointer to emphasize that. There's 2016, here's 2017, here's 2018, right there. And what you see is that 2018 evidently is, it says, the fourth hottest year on record. Well, that seems to work because there's 2018, 17, 16, and 15. So it looks like indeed 2018 is the fourth hottest year on record. The obvious question then is, okay, what was going on? And you can see that there was a period back here when things were fairly flat, and then there was a steep rise at the early part of the 20th century, a flat piece, and then a continued rise toward the end of the 20th century and into the 21st century. So those are data taken, those are average world temperatures, and one can talk about how those are collected, but for the moment, that is a good assessment of where we are with regard to average temperatures, average world temperatures in the world. Okay, so let's move on to see what happens next, and that is what about 2019? Well, interestingly, 2019 are the black dots, and it's very hard to interpret this, so I will interpret it for you. Up here, what you see at the very top is an orange line. And oops, sorry, go back. Orange line right here. See the orange line here? Orange line is 2016, and by any measure, 2016 was the hottest year, indeed, that we have had in recent time. These are the records. 2016 is the hottest by far of any of the previous years, including all the ones down here from the 20th century. And then there's this little black thing moving along here. There's January, February, March, April, May, June, July. Interesting. August is missing. Well, it's an interesting detail that it turns out that July was the hottest month on record in the world. Okay. August was the hottest month. I beg your pardon. I start again. I misquoted. July was the hottest July on record. Period. August this year was the hottest August on record. So we can then look to see where that little dot is going to go, and the answer is that little black dot here is now going to move fully up to about there, where August belongs. It's saying that not only have we exceeded what was going on back here in 2017, but we're actually doing even things that are hotter than 2017. So we're moving in a direction that looks as if 2019 may very well be the second hottest year. It's conceivable it might be the hottest year. That little black line went all the way up to here. Unlikely. It looks as if 2019 will be the second hottest year on record. Okay, so that's not good. If you go back 1,000 years, just quickly to take a look to see where we are, this is looking back all the way to the year 1000, the year 2000, roughly speaking. The wiggly lines are different ways of looking at measuring temperatures. They're called proxies. It turns out that there was a period back here in the early 12 and 1300s when there was a medieval warm period. There is a mini ice age here when things were considerably cooler, and that black curve represents the one we were just looking at a moment ago, where we had a steep rise at the beginning part of the 20th century, a flat part in the middle, and then a steep rise at the end, and here's 2018 up here, you can see. So I'm worried that my next slide will just have to be different, because my 2018 will fall off the edge. Okay, enough about temperature. Temperature is rising. And now let's talk about the second piece of information. First, about temperature. Are you all right? Do you understand what's happening? Okay, so let's see why. Let's take a look to see what is happening. And there is one piece of information that I'd like to transmit to you or discuss with you, and that has to do with the whole idea of the greenhouse effect. Greenhouse effect, in a nutshell, has to do with something called infrared radiation. Well, infrared radiation is being illustrated here. There's Cynthia in her office, and what you notice about that picture is that there are hot spots and there are cold spots. The hot spot, there's a hot spot right there, which is the temperature of her neck, and if I look over here, I can see that her neck is getting pretty close to 37 degrees Celsius, which is 98.6 degrees Fahrenheit. Are you surprised? No, it's roughly your body temperature. You put your hand there, it's roughly about what you get, okay? You'll also notice that, that there are cold spots. Interestingly, well, I won't dwell on this, but dwell on that, but there's a little hot spot right here on the page that she just recently turned. So you can tell quite a bit from an infrared photograph. It's really kind of nice. Okay, so what's happening is that the sun turns out to produce a certain amount of light. Some of the light is in the visible portion of the spectrum, and some is in what is called the infrared. And this piece right here is the visible piece. This is ultraviolet over here. Visible piece goes from violet all the way to red, and then there's this long tail, which is an infrared tail of radiation. And it's that kind of stuff that you can see with an infrared camera. Fine, so it turns out that evidently hot objects glow. Cynthia glows, you glow as you radiate light. Turns out I can't see you because you're not radiating visible light, but you're emitting radiation which is called infrared light, so let's take a look to see what you're radiating. Here's that same curve for the sun, there it is. That's the sun's spectrum, to be assured on the log scale, which you can ignore for the moment. And here is your spectrum. That's the radiation that you give off. Okay, so your radiation is way the heck out here in the infrared portion of the spectrum, and the sun is radiating both in the visible down here and also in the infrared portion out here. Okay, fine. So you have two radiators, and the question then is, how do you get global increase in temperature? Well, the next band all the way across represents the atmosphere. There it is. The atmosphere can either absorb most of the radiation or not absorb the radiation. Here's a nice clear window which says that most of the visible light actually can pass through the universe, can pass through the atmosphere without being absorbed. Happy with that? If you look on a clear day, you can see the sun. That's a good sign. Okay? If you can see the sun, it means you're actually able to see that the atmosphere does not, on a clear day, absorb much of the energy. A little bit, yes. Now let's go over here to the part that's trying to go back out again. This is the stuff you're radiating, which has to get back out into outer space again. If we're going to have a balance, notice that the amount coming in has to equal the amount going out. If those two are not in balance, then you'll get an increase in temperature. Okay, so let's put the two in balance. And what you see is, yes, there's a nice window over here, which is allowing the sun's visible energy to come in. And then I look over here to see whether there's a nice visible window for it to go back out. And the answer is yes, there is a window, but it's not completely open. In fact, I notice nasty little humps over here. That little hump there, which is tending to absorb radiation, is coming from nitrous oxides and methane. That one's coming from ozone. And this one over here is coming from good old CO2, carbon dioxide. So what's happening, lovely folks, is that that little peak right there, as we increase CO2, is getting bigger and bigger and bigger. And as you fill it in, you begin to make it difficult for radiation, infrared radiation, to get back up. That's complicated, but that's it. Okay, are you happy with the basic idea? Incoming radiation, outgoing radiation, the two must balance. And if they don't balance, it can be due to a very small change in something like carbon dioxide. So let's look at carbon dioxide quickly. Carbon dioxide is increasing from 1960 up to 2019. In fact, 2019 and all the way up to August. It turns out the September data is not in yet. So on August 2019, there are 409.95 parts per million of CO2 in our atmosphere as measured by Mauna Loa. And there it is, the wiggly line going up and down shows indeed that CO2 does go up and down. We could get into that discussion. We can come back to that as necessary. If you look in the long range to see what's happening to CO2 over the last 1,000 years, there's a kind of an interesting thing happening, and that is that CO2 was pretty constant for a very long time. Roughly, in fact, it's been constant for the last 10,000 years-ish, and then suddenly about 1800-ish, it begins to deviate and start to rise rapidly. And indeed, the good old Industrial Revolution back here in about 1700 in England, actually 1650, began burning lots of coal. We joined the group here, and lots and lots of coal is being burned here. And now the amount of CO2 in the atmosphere is that number we were just looking at, which is 410 parts per million. So something funny is going on, lovely folks. It's not funny. Something interesting and dynamic is going on. And so there are two things we've done. We've seen temperatures rise and we've seen CO2 increase. I'm getting close to the end of this, the end of my time, I realize. Okay. So what's happening? Well, the CO2 is coming from two sources, mainly 90% from burning of fossil fuels, another 10% from land use change. If you cut down trees, for example, those trees will then eventually disintegrate because of all sorts of little buggies, and the bugs will produce CO2, and then that adds to the total CO2 in the atmosphere. So roughly 100% of CO2 that we as human beings generate is coming from this side. If I go to the other side to see where it goes, about half of it goes to the atmosphere, about a quarter goes into increasing the rate of growth of trees, and the other quarter goes into acidification of the ocean. You will hear more about that as time goes on. So I have just 5 minutes left. Okay. So what happens then when you burn fuels, coal being among them? Coal is more than 50% carbon. Even the hard coal can be as high as nearly 100% carbon. If you combine it with oxygen, you get carbon dioxide. Okay, so that's clear and easy. There is on the Wabash River, you can see down here, there is a little red dot, and the little red dot represents one of many power plants on the Wabash and the Ohio rivers, and so Indiana is a contributor to these things. Okay, one of the things you're going to hear about is, from Paul, is the whole business of long range. So I'm not going to spend much time on this except to point out that, that the amount of carbon you put into the atmosphere matters. And that it matters because if you continue putting CO2 into the atmosphere, you can raise the temperature of the Earth by a fairly predictable quantity. Now that's not quite fair, but it's a fair statement that if I were to do something really silly, like continuing to put CO2 into the atmosphere here along that red line, it's called business as usual, then I could indeed reach temperatures that would be astronomically large. 4 to 6 degrees C is in Fahrenheit degrees, getting upwards toward 7 to 11 degrees Fahrenheit, which is just an incredibly world, one we don't want to do. If you want to limit yourself to something less than 1.5 degrees, it looks like the blue curve is the one you want to choose down here. That's fine. So where are we right now? Well, here's 2020, right? We draw the line up from 2020. 2020 goes to here. Actually, it turns out we're just about there, a little bit below the red line, just a tad below the red line. It's good we're below the red line, but not much below the red line. Okay, so we're really not doing what we want to do in that regard. This simply is a rather dramatic way of looking to see where we've been. Here is our CO2 rising, and here is where we need to be in order to limit the total increase in temperature to 1.5 degrees. That would be, is it something that's going to be really easy to do? No, it's not going to be easy to do. We're going this way. It looks as if we did business as usual here, and rather doing something like that, which looks to be difficult at best. Okay, finally, that was whether it would be a good idea to have a glass of water up here. It would have been a good idea. I said, no, don't bother. Okay. Yeah, thank you, Ron. All right, so two things under control, temperature and CO2. Well, we want to go and fast. That has to do with fuel, and thank you very much. It turns out that the major source of CO2 is coming from the burning of any of the carbon fuels. Coal turns out to be the nasty one because it's almost pure carbon. And so yeah, I can ask then about world resources and just look to see how much coal there is in the world. And the amount of coal in the world is enormous. You'll see here in gigatons of carbon, the amount of coal is 12,000 gigatons. Oil, 10 times less. Gas, 10 times less. Total 14,000 gigatons of CO2 producing fuel that is available. Okay, that's interesting. On the other hand, how much of that has to stay in the ground, indeed, in order to stay below 1.5 degrees, below 2 degrees actually? It turns out we're allowed to use 1,100 gigatons of that, and we have then, lovely folks, a problem. And this problem is going to lead you to my summary. Carbon fuel resources, our total available fuel resource, green coal is large, available, and cheap. Business as usual means that we will reach 1.5 degrees by 2030 or 2052, and we will actually be at 2 degrees by 2060. The collateral damage from floods and storms is huge. And so those are the conclusions I draw from my piece, and now we have 4 magnificent people who are going to talk to us about the details of this problem and what to do. So I think what I do right now is introduce Paul, and Paul will jump up. Oh no, Michael's going to do it. There we go. Excellent.
I think we're going to do Who wants to take environmental physics with our true hero, Indiana? That was a wonderful introduction to the physics of climate change. So why don't we bring all of the panelists up here? So as we did last time, we've got a beautiful overview presentation, and now we have 4 experts in different aspects of environmental issues and environmental stewardship. So we'll start with, again, I'm going to ask you guys to introduce yourselves a little bit. Paul Staten is a member of my department in Earth and Atmospheric Sciences. Is going to speak about climate modeling. Kim Novick from the O'Neill School of Public and Environmental Affairs is an expert on atmosphere-biosphere interaction. Ellen Ketterson is a superstar of the bird world, distinguished professor of biology at IU, and the founding director of the Environmental Resilience Institute. And Gabe Filippelli, who's come all the way down from IUPUI, is a professor of earth sciences and the director of the Urban Health Institute, and an expert on the intersection of environment and human health. So I think we're going to go in this order and turn it over to Paul first.
Get your mic, Paul. Get your mic right there.
And yes, and remind everybody that you can text questions either for Ben or for our panelists at the same text number.
Pull it right out. There you go.
Thank you, Michael. How do I answer this line?
Oh, it's in my hand.
Press the mic, put it in that pocket. There it is. All right, so I'm Paul Stake, and I work in the Earth and Atmospheric Science Department, and I really enjoy studying the Earth's planet system. I'm one of those types that I'll be walking by a pond or something, and the reflection just catch me, and I'll stop and stare. I love fluids, I love what I call dynamics, and I can do it all day. So I find climate change actually a very fascinating thing to study, which may sound odd to say, but I like to play with models. I play with them all day. You know, why do we model anyway? Well, anytime you want to do something for the first time, you probably want to think about it first. And if it's going to be expensive or involve a lot of people, you probably want to think really hard about it or model it. So for example, if you're building an airplane, you probably want to build a model of that airplane and include like how the wind stresses different parts of the airplane, how much lift it's going to get. Or if you're going to build a bridge, you're going to put this bridge into a model first, and this model's going to have like the properties of the materials of this bridge baked into the model so you can understand how that bridge will behave. Or if you're a country like the United States and you need to maintain your stockpile, but you can't afford to simply go drop a bomb every few weeks to test everything, you model your stockpile. And you take, we have field measurements from past explosions. We take lab measurements all the time, and they have models to make sure the stockpile is still healthy and good without the cost of dropping bombs. Now, if you have a model and you have a bridge or a design in your model, and the model says this design is going to fail, that's not going to get built. Now, if an engineer designs something and the model says this won't work, and the engineer says, well, I think it's the model, actually. I think the design is great. I think it's the software. Now, if the engineer had two different pieces of software, they both said the same thing, that bridge isn't getting built. So, with the Earth system, we model the Earth system too. Now, how does an Earth system model work? Well, the Earth system model is built on laws of physics. So instead of stresses on the airplane wing, it's stresses that different parts of the atmosphere push on each other. When you push on things, they tend to move unless they're heavy and they don't want to move so much. Lab experiments, like the properties of a bridge, we have the properties of carbon dioxide. We know what kind of light carbon dioxide absorbs, and so that tells us a lot about the greenhouse effect. And we use field measurements. So it's like with the nuclear model, it's informed by past nuclear experiments. Our Earth model is informed by field experiments we run today. Like we'll fly through clouds and we'll measure how clouds form. And all these physics and these experiments and measurements are baked into an Earth model. And does it work? Well, actually, it works really good. We use these models all the time. And you could say we bet our lives on them. Hedge funds, investment firms bet millions of dollars on these models. Now, of course, I'm showing you weather right now, not climate. And you don't have to have a climate model doesn't have to be a good weather model to be a climate model, but it's nice. And of course, there is a difference between weather and climate, and my favorite analogy for this is actually a match. So if I take a match and I go up against this box, it should light, right? Oh, good, all right. Lights up, a little phosphorus. And if I were to light another match, they would both flicker. But that second match, good match though it is not going to be able to predict the flickers of this match. They're not going to line up. Now, if you had a good model, you might be able to predict one or two flickers, but can anybody in this room predict every flicker of this match? No, you really can't. But what can you predict about this? Ow! You don't have to predict the flickers to understand how a match behaves. And so, yeah, climate models work really well. And many climate models, Europe's climate model, they actually have their weather models, they are their climate models. They do both. So climate, you tilt the match up, it's going to behave differently. And that's basically how climate models work, even if weather is really hard to predict a couple flickers in advance. Back in 1965, the advisory committee to LBJ told them, hey, look, by the end of the century, CO2 is going to be up, temperature is going to be up, and it could have potentially deleterious effects, and we should do something about it. The climate models we started running in 1967, have predicted what we see today, and we were right. And you can even use these models. They're so good. You can actually change the measured numbers to match other planets, and you can understand the climate on other planets. Because even in a warming climate that we've never experienced before, the laws of physics are the same. And this is what we can expect from our climate models. By the end of this century, it's going to be warmer, or it's going to be really red, and really red looks scary. I don't want that. And then UN report you heard about earlier, a couple centuries from now, the ocean could be a whole lot warmer and sea levels could be a whole lot higher, or it could be a fair bit warmer and a fair bit higher. I want that blue curve. And the good news is, we're holding the match. Thanks.
I'm sorry to disappoint, I did not bring any fire. My name's Kim Novak, let's see if I can get this working. Michael told us we were supposed to introduce ourselves sort of personally, maybe tell our personal story of how we ended up here, and I don't do that very often. I didn't have an answer. I thought about ignoring the instruction. Instead, I thought about it, and the answer, why I ended up in the position I am, I studied land atmosphere interactions, is that I like math. I liked math when I was 10. I liked math in high school. I liked math in college. I liked math in grad school, and I like it now. And when you're in grade school, or high school, you know the math is maybe you're aiming towards a certain target, right? The answer's in the back of the book. And so it's simply a matter of lining up the rules and the equations until you get to the answer. And it's fulfilling when you do. But once you get into grad school and beyond, there's no answer in the back of the book. Right? And so you don't really know where you're aiming. There's no guarantee that an answer even exists, and there may be more than one right answer. But still, mathematics is a useful tool for extending our common sense, right? Taking our principles of how we know the world works. In my world, that's conservation of mass, conservation of energy, conservation of momentum, right? And lining them up. And every now and then you get lucky. And you line them up the right way, and you can explain a problem that you didn't know the answer to before. And that is such a good feeling. So I know enough about math to know not all of you share my enthusiasm for mathematics. Maybe you have other ways of extending your common sense and other ways of lining up rules and principles to help you feel good about solving a problem. And I think it's important because there are some climate scientists that are very vocal in prescribing their ideas about what we should do about climate change. I want to tell you that the vast majority are really nerds like me and Paul, if you don't mind if I lump you in there. I don't know about Owen, I'm pretty cool. I go to the cool. But we don't come with an agenda, we just love math and science. All right, so I study how do climate and weather affect ecosystems, and I study how ecosystems affect the rate of climate change. I came to this from a degree in civil engineering, which resides on the strong foundations of how fluids move through the environment, including both air and water, which are key fluids in governing our climate system and how it interacts with ecosystems. And so my lab in particular uses these nifty tools called flux towers. This one's in Morgan Monroe State Forest, and that's the view from the top, which allow us to measure all the time how much carbon dioxide is moving between the atmosphere and the ecosystems, how much water is being used in the process, what are the energy fluxes, these radiation fluxes that Ben was talking about, what are the effects on surface temperature, and so on. We have great toys and great tools, and we're often up in the air. How do climate and weather affect ecosystems? Well, there's good news, there's bad news, and then there's other news. In fact, climate change in particular, and in some cases, in isolation, in some ways good for ecosystems. It promotes longer growing seasons and puts more CO2 in the atmosphere for the plants to use for food. But also causes more droughts, more floods, both of which are bad news for agriculture. We saw the case of more flooding and excessive wet periods this year. We saw the case of an extreme drought in 2012. And then it also brings complicated problems, more disease, more pests, more invasive species, which pose threats to ecosystems. If you want to know more about how climate change will impact Indiana in particular, you should check out this report put out by our friends up at Purdue, but in collaboration with many scientists at IU, that walks through a number of impacts of climate change specific to Indiana. What does it mean for ecosystems? It means we got the bad and the ugly tend to overwhelm the good. right? Most of my field for decades has done a great job of identifying problems. We have got a lot of problems, right? Every day a paper comes out, another problem. Yields are gonna go down. Droughts are gonna get worse, right? This insect's gonna come in. This weed's gonna come in. This pest is gonna come in, right? These are all feedbacks that accelerate the rate of climate change. They're real problems and we need to understand them. But after a career so far studying problems, I do find it refreshing to sometimes think about solutions. And so one that my lab's been working on is looking at actually historic changes in forest cover. This is in Indiana. Long story short, used to be covered in trees, then there were no trees, and now there are a few more trees. And so we've studied in particular this period, this century of regrowth over the past century in Indiana and the entire eastern United States. And I can tell you two things about this period of regrowth, which happened when farmlands were abandoned naturally, and also with substantial help from the Civilian Conservation Corps, which was a New Deal program. These forests now give us a large discount on our fossil fuel emissions. They take out 40–50% of our CO2 emissions in the eastern United States, get reabsorbed and stored long-term in forested ecosystems. Right? Without them, without that uptick, climate would be changing faster. They also cool the surface. They use more water than nearby short-stature ecosystems. Just like when we sweat and we evaporate, it's a cooling process for our bodies. When the land uses water, it cools the surface. And we've also been able to show that this cooling benefit extends to the nearby air. Right? So this is a way that we can address, locally at least, some of the more deleterious effects of climate change. Now, we could reforest the entire state of Indiana and the entire eastern United States, and it will not stop climate change. It will help. We can do all sorts of things that in isolation will not stop climate change. If we want to keep that limit to 2 degrees C, or even better, 1.5, we're going to have to throw the kitchen sink at it. Okay? There is not one thing, no magic answer. But the good news is there are a lot of things that we can do. This is a list from a website called Project Drawdown, drawdown.org. You can go there and read more about all of the things that can have a substantial impact towards limiting warming to 2 degrees Celsius. There's really something here for everybody, I think. But it's a complex problem that has many solutions.
I'm missing seeing these slides, so I'm envious that you all can see. My name's Ellen Ketterson. I'm in the biology department here at IU, and I study birds for a living. And I want to share with you some of the recent findings about how we're losing birds, and we're losing them rapidly. And then it's not just birds. As you'll see, there are a lot of people who care about birds, and so we have more information about them than we do about a lot of the other species who are also disappearing as a result of not just climate change, of course, but all of the environmental alterations that we can attribute to ourselves. So, what does a person do? Okay.
Ready?
Yes, I'm ready. We have a 1-minute video here. Paper came out last week. We've lost 3 billion birds in 50 years. Not just rare birds, common ones too. And we can tell by radar tracking. Grassland birds are especially challenged. These little burrowing owls are the biggest thing you've ever seen. And we're having a lot of impact on the environment. Waterfowl are an exception. If you go to Goose Pond, that's an area where we can put more wetlands, and birds are responding to what we've done. And birds are important. They pollinate, they disperse seeds, they eat insects, control pests. And this meadowlark, with its beautiful song, is one of the ones that we've seen really go up now. So, I'll show you a data slide next, and I'm There's 3 parts to the slide, A, B, and C. And the data came from a paper that appeared in Science last week, and Science is our pinnacle journal here in the United States. So the x-axis is how many birds have been lost, and the x-axis is year, and the y-axis is how many birds have been lost. So on A, on your left, that's all the birds that have been lost, not broken down by where they live or what kind of bird they are. But since 1970 to 2019, 3 billion. That's 3 billion out of 10 billion. And I've heard others say, and I feel the same thing, I feel an ecological grief about this loss. The middle one breaks down the losses by where birds live or what kinds of birds there are. So I won't try to go into this, but the blue line that goes across the top of the middle graph, those are water birds. Those are those mallard ducks that we saw in the video. And we don't really see a big decline in water birds because we've actually given them more habitat over this period of time. But the bitter losses, the ones that go way down, are the ones that were also shown in the video. So those are birds from the grasslands, those are birds from the tundra, those are birds from the boreal forest. We're right there in the middle, so if we just take the forests that Kim was talking about, the eastern deciduous forest that is Indiana in its history, then we're the green lines that are going up above the middle. But we have indeed lost a great many birds right here, and particularly any prairie species. And then on the far right, I won't try to show you that, but again, it just breaks it down by kind of bird. And a few are showing increases, but all of those bars to the left are declines in abundance. So how do we know, right? You always want to know. It's in the paper, it's in the very best journal. That might be sufficient answer, but most of us, I think, want to have a little bit more knowledge about how we know things. So there are, as it turns out, about 43 million bird watchers in the United States. That's a lot of money, actually. They buy binoculars, they buy bird seed, they buy bird feeders. They're folks like me, and they may be folks like you. And some of them are really just watching birds for the recreational value or the beauty of them. But some of them are citizen scientists. They're people who go out seriously. Oh my goodness. Okay, I'm talking faster. They go out and they run surveys. So they run surveys around Christmas and they run surveys in the summer. And they report their numbers following a protocol that everybody that's participating in the surveys does the same thing so that the numbers are reliable. These are good people who can identify birds and identify how many they're seeing. And that's the basis for saying we've lost 3 billion birds. That, over those 50 years, in addition to the radar data that you saw ever so briefly in the video. So I can tell you really quickly why I came. I'm a witness. I'm here tonight as a witness. I'm a witness to the empty skies. So I'm 74 years old, and those bird numbers and the decline of the 3 billion, that began when I was in graduate school. That began when I picked a particular bird to study. It's called dark-eyed junco. There are 186 million fewer juncos in the world than there were when I started to study them in 1970. When I sit on my deck, I don't see the chimney swifts that were always in the sky. I don't see the nighthawks this time of year that should be flying south. I don't see whippoorwills or hear whippoorwills in the morning as I did. But there's a changing baseline. If you're a lot younger than I am, you can't report that because a lot of those losses will have already occurred. Hence, it's kind of a duty or responsibility while I have the opportunity to tell you what my personal experience has been and to say we really need to make a change for those who follow us. Because even if you're young, you'll be followed. So I think it matters because nature provides for us. The video told us that birds provide and other wildlife, ecological services like pest control and seed dispersal and pollination. So birds are our smoke alarm, and we can turn this around. You can keep your cat in. You can put something up on the windows that will make it less likely to have a collision. You can take your kids to McCormick's Creek on Sunday and let them hold a bird if they're lucky enough to catch some. You can speak up and speak up and speak up because you're a powerful person. Every one of you is a powerful person, and people will listen to you if you report to them what you observed while you still have an opportunity to do that. I think we have an obligation to respect what we were given. And then finally, one little note of hope. So these are museum skins. Ornithologists go out and they collect birds, and then they prepare skins so the future ornithologists can measure them and learn about them. And the bird here is a horned lark. Horned larks have white bellies and yellow throats, and that's the way they look on the right. On the left, those are also horned larks, but those horned larks have soot. They have carbon stored in their feathers because they were made into skins 100 years ago from Rust Belt cities. The ones on the right were made into skins just in the last 10 years. So we have cleaned up our act. We do have cleaner skies. We can pull together to make a difference, and that's our job. So.
My climate crisis came 30 years ago when I was a Peace Corps volunteer in a small island nation in the middle of the Pacific Ocean called Kiribati. 1988, Kiribati is an atoll at sea level, and it will prove to be one of the first victims, nationwide victims of climate change because of rising sea levels, from what we heard from Ben and others. Now, 30 years ago, it was no surprise to the people of Kiribati that this was going to be a big problem because it was plastered all over their national magazine. Island sinking, Kiribati gone in the short term. So that was my initial introduction to how climate change can impact the health, in this case, of an entire nation. Fast forward 30 years. So what have we done in 30 years? 1988 happened to be the exact year also when James Hansen, at that time from NASA, gave the first alarming testimony to Congress about the threat of climate change, not just the threat of the future climate change, but that it was already happening. So 30 years. So we've known about it for 30 years. And what's happened? Well, in all of Earth's history, all of humanity's history, we've burned half of the carbon that is in our system since 1988. So the answer is nothing has happened. And so this is why you hear these impassioned cries to turn that dial. So fast forward to me 2 years ago when I was the lead author of the Purdue's climate change assessment focusing on health impacts. I could stand up here and tell you all of the bad health impacts because, trust me, we poured through all of the recent history of climate change in Indiana as well as projections that we've seen that Ben and others produce. It's all bad news. More ticks, more mosquitoes, more tropical diseases, more heat stress, and so forth. I prefer to focus on the better news. And I think that the country of Kiribati and its future, which is bleak, nevertheless, has some good answers for us on what is the positive on all this. It's no question that Kiribati as a nation will be finished in 20 years. They're a sovereign nation, member of the UN, they speak their own language. They will no longer be able to live on the island, not because the islands will be completely flooded by a sea level rise, it doesn't happen that fast, but because the very precious freshwater lands that they depend on will be destroyed because of incursions of brackish water. And brackish water leads to a whole bunch of health effects, right? And they do not have any electricity, they don't have any capacity to desalinate or ship water. Yeah. So there are some climate victims that we'll just simply have to call climate victims, but use their story as inspiration for how we can change. And their story is this: they are a poor nation, they didn't contribute anything to climate change, but they are also the least able to adapt to it, right? So it's a bad three combination. The countries that contributed most to climate change, the West, the developed world, has the most ability to do two things. One of them is adapt, and the second one is to stop emitting. Right? We have the capacity to do both of those, to adapt while we sharply reduce emissions, so we can be on Ben's positive side of the curve. So I think that the nations of countries like Kiribati, whose national health depends on us solving this problem, are looking to those very countries that contaminated the atmosphere to solve the problem. And I don't mean solve it for us. Frankly, the United States, other than the biota, the United States is actually going to be pretty stable through most projections of climate change because we are rich enough and we have adequate infrastructure. But we need to start thinking about not just using that infrastructure to improve us. We need to use that infrastructure to produce solutions for those countries that are most vulnerable to the health impacts of climate change. So I think there's a lot of hope and promise in some of the things we've been saying, even if it seems a little bit depressing. And that hope and promise, I can rely on the people like Kiribati to continue, the people from Kiribati to continue cheering us on. So thank you very much. That's all I have to say.
All right, thanks to all of you, and thanks for giving us some time for questions and answers and discussion. So if you haven't yet done so and you want to, you can text in some additional questions. We'll do a few now, and then we're going to have some time for discussions at the tables. I think one good one to start with is maybe one for Paul, or maybe for Ben also. It's a question about solar variability. How did the climate models take in the question of variability in solar insolation here?
Fantastic. One of the things that you plug into the model of the Earth is you plug in how strong is the sun today, and a lot of scientists like to actually play with this, so they can modulate the strength of the sun. The model, they can watch its effects on the atmosphere. In particular, the solar cycle, every 11 years or so, you get this little bit of an increase, a little bit of decrease with the intensity of the sunlight, and you can see its effects in the Earth system, but it's just 11 years, and the effects are much too small to, are very small compared to the impacts of climate change now. But yeah, in the Earth system model, that's one of those numbers that you plug in, and you can run all kinds of experiments with it. So that's definitely one of the really important pieces to investigate, and that's one of the first stones we turned over back in the 60s and 70s when we were starting to see, wow, we're warming and CO2 is going up, but is the warming because of the CO2? The solar cycle was one of those first stones we turned over.
Okay, Ellen, you succeeded in getting a lot of bird questions. So one very basic one is how, to what degree birds and other species can accommodate changes in temperature and essentially migrate their way through climate change stresses.
Right, I'm looking at my friend Adam Kluger because that's a question that we're actually trying to address. So how can I say how plastic is the timing of a bird in terms of when it migrates or when it reproduces, and so if it's warmer, it might just leave earlier and breed a little bit farther north, and maybe it would be just fine. Lots of data suggests that everything is not just fine, but it is a way of thinking about it. The other is if they need to evolve their way to change genetically in order to be able to accommodate changes in the environment, that's a slow process, a slower process. And hence we would be worried about whether or not populations could keep up with environmental change. And I think some of these losses suggest that keeping up may have been already proved too much a challenge for some species.
And maybe a related question, can you separate the effects of climate change from habitat loss, from environmental pollution or other stresses?
Oh yeah, that's totally important. I don't mean to suggest that all 3 billion of those birds went away because the climate's warmer. So the climate's warmer, everything we've heard tonight is true. But the challenge is for birds go beyond the timing of reproduction or the timing of migration, or whether it's too hot when a female's sitting on her eggs. So habitat destruction and pesticides and collisions and cats, those are multiple sources of mortality that have gone up and hence help to contribute or explain the decline in numbers.
Okay, and maybe this is one for Kim. There's a question about harvesting and replanting trees and its effect on the carbon budget.
It's a great question. Longstanding ecological theory used to be that when it comes in terms of the forest's ability to take carbon out of the atmosphere, that there was a peak around 30 or 40 years, and that by the time the forest got to be 100 years or so old, it was no longer a carbon sink. And this is an exciting question that the scientists I work with all around the country have been able to answer with our very fancy meteorological flux towers. That the theory does not appear to be correct, or at least the x-axis is wrong, that even our 100-year-old maturing hardwood forest, because the hardwood forests around here are almost 100 years old now, are still quite strong carbon sinks. All right, so there's no need to harvest, right, from the perspective of taking more CO2 out of the atmosphere. But planting more would help. I don't know if that was fully addressed the question. I'll be happy to chat later if it didn't.
And I think there's one for you, Ben. There's a question. You showed the plot of the temperature records from 1000 to 1900, followed by the more recent instrumental record. Can you say a word about how that temperature record was created?
Indeed. It turns out there is something which you and I know, and that is there are lots of different ways to measure temperature. Many different things depend on temperature, including things like the rate, for example, of, think tree rings for a moment. If you think about the way a tree grows and how thick the layer is that you get from a given year, that thickness depends on a couple of things. It depends not only on temperature, but it also depends on water. And those things are oftentimes closely coupled. What you can do is you can untangle those two effects, and you can actually use then tree rings as a proxy for annual temperatures. You can also use, for the cavers among you, you can actually look at the way water flows in the cave and the way it then forms stalactites and stalagmites. You can also look at creatures in the ocean. Most of the shell creatures in the ocean produce annual rings or semi-annual rings, and you can actually look at the widths of the rings to tell you a good deal about temperature of the water in the ocean. So there's several strategies that you can use. My guess is that almost everything we think about depends on temperature in some level, and so if you work it backward, you can actually figure out what the temperature is that corresponds to where that thing is living.
Super. You didn't mention that you can use those proxies to tell about prehistoric earthquakes as well. I gave a question for you. You're the director of the Center for Urban Health. Can you say a little bit about the differential impacts of climate change on urban versus rural areas and how that affects the health of communities, say in Indiana or elsewhere?
Sure, and I'll use, it's an excellent question. I'll use a lens of Indianapolis for that, because we're specifically doing our Grand Challenge effort on resilience of cities. What we find is this very strong correlation between, in cities at least, those areas that are most environmentally vulnerable, meaning vulnerable to kind of the worst impacts of climate change. And in cities, it's usually heat stress and flooding, which are both the drivers of the most morbidity and mortality from climate-related issues in cities. It ends up that there's a very strong correlation between those areas actually that are vulnerable to both of those and those areas that are lower income and often lower income communities of color.
So it's the same story again, that the ones least responsible for the problem are the ones who face the biggest effects. Well, that's wonderful. How about a round of applause for our speaker?